Hi, in this video, we are going to look at a technique called interpolation and also the method of differences of polynomials. So let's get started with the idea of Lagrange's interpolation. So basically, given n different x coordinates, n different x coordinates, x1, x2 till xn, and the corresponding y coordinates, the corresponding y coordinates y1, y2 till yn, we have n different points in the coordinate plane, n different points in the coordinate plane, and the points are basically x1, y1, x2, y2 till xn, yn, right? The interpolation problem is basically to find a curve that passes through these endpoints, that passes through these endpoints. So that is the idea of the question. Now, obviously, there are an infinite number of possible curves that will satisfy these conditions. Infinite number of possible curves like this. However, what we want to do is to find a polynomial f of x, with lowest possible degree, that satisfies, that passes through these points, through these points. So the general interpolation problem has infinite number of solutions. There will be many possible curves that can pass through these endpoints. What we want to find out is, can we get a polynomial which can be made in such a way that all of these points lie on the polynomial, right? So these n points can pass through the polynomial, and we want a polynomial of the lowest possible degree. So Lagrange figured out a formula which can help us calculate this. So Lagrange's interpolation formula basically says that there is a unique polynomial f of x, whose degree is less than or equal to n minus 1, that passes through these endpoints, to these endpoints. And what is this polynomial? The way we find the f of x is this way. F of x is going to be equal to y1 times x minus x2, x minus x3, product till x minus xn, divided by x1 minus x2, x1 minus x3, product till x1 minus xn. This was with the y1 point. Then we take y2, and now the missing factor on top will be x minus x2. So you'll get x minus x1, x minus x3 till x minus xn, divided by, in here you put x2 minus x1, x2 minus x3 till x2 minus xn, and so on. You will keep taking the points. So finally you'll get yn times x minus x1. The factor missing on top will be x minus xn, x minus x2 till x minus x of n minus 1. And then you will take xn minus x1, xn minus x2 till xn minus x of n minus 1. So this sequence of sums basically gets us the polynomial f of x, which will pass through all of the points x1, y1, x2, y2 till xn, yn. And the degree of the polynomial can be less than n minus 1, but maximum possible degree is n minus 1, right? So if a polynomial has degree n, you should know that if polynomial f of x has degree n, it is uniquely determined by n plus 1 points. These points should be different from each other. So basically, the way you say that a circle is uniquely determined by 3 points. In that way, a polynomial of degree n is determined by n plus 1 points, and Lagrange's interpolation formula gives us a way to figure out that f of x, right? So when we do examples, we'll see how to apply this. The next topic that I want to discuss today is differences of polynomials. So that will turn out to be related to Lagrange's interpolation later when we use it in questions. So for a function f of x, and a fixed h not equal to 0, we call f of x plus h minus f of x is known as the first order difference of f of x with step size h. So what is the size of the difference? The step size is h, and this is called a first order difference. And the way you usually denote it is delta 1h f of x, or simply sometimes delta 1 f of x, when it is understood that the step size is h, right? So this is a symbol to denote this difference, first order difference of f of x. Now, if you take the difference of delta 1h f of x, so you're taking the difference of, already it was a first order difference, right? What you would get is basically delta 1h f of x plus h minus delta 1h f of x, right? Basically, you're applying the definition of first order difference to an already existing function, which was a first order difference itself, right? So this would become basically f of x plus 2h minus f of x plus h. The first term here is breaking out to be this, minus this is f of x plus h minus f of x, right? So basically this turns out to be f of x plus 2h minus twice of f of x plus h plus f of x, right? And this is known as the second order difference of f of x with step size h, right? This is second order difference. We are getting this expression. Now, the way you define it is a recursive definition. The second order difference comes by taking a first order difference of an already existing first order difference. So in a similar manner, we can define delta nh f of x, which is the nth order difference of f of x. And how do we define it? It is taking a first order difference of an already n minus 1th order difference, right? And how do you evaluate it? You will calculate this and you will write it as first order difference of already n minus 2 order difference, right? And so on. Eventually, you will get a first order difference of a first order difference of f of x, right? In n steps, you will be able to figure it out and you will get the final expression, right? So you can show by induction, or you can actually try and evaluate it. The better method is induction. You can prove by induction that delta nh f of x, the nth order difference of f of x with step size h, can be given by the formula summation I goes from 0 to n minus 1 power n minus I nci times f of x plus ih. So basically, I goes from 0 to n, and this is the sum of these terms. So think about it. The first term here would be what? When I is equal to n, you would get ncn f of x plus nh. And the next term would be plus minus 1 power 1 ncn minus 1 f of x plus n minus 1h, and so on. The last term will basically be when I is equal to 0, you get minus 1 power n nc0 f of x, right? So this is the overall expansion. Notice that it looks similar when we did a second order difference of f of x. We got f of x plus 2h minus twice of f of x plus h plus f of x, right? Notice that this will fit the formula. If you put 2 here, what will happen? It will be f of x plus 2h here. This will be 2c1 and minus 1. So minus 2 f of x plus h. And finally, this term will be plus f of x, right? So the formula is correct. And you should remember this result. This is a standard result. This is the nth order difference of a function, right? Now what we'll do is we'll apply this to a particular problem. So we'll say, let f of x be a polynomial of degree m. So let's write f of x as am x power m plus am minus 1 x power m minus 1 and so on till a1x plus a0. Now in this case, the nth order difference of this function will become a polynomial of degree m minus n. M was the degree of the original function, and we are taking an nth order difference. So the polynomial of degree m minus 1 will be this nth order difference as long as n is less than equal to m. If n is greater than m, then the nth order difference is identically going to be equal to 0. If the difference order is greater than the polynomial's order, obviously the difference will be 0. Now, if you calculate it out, you can verify these claims. We can say delta 1h for f of x will be simply f of x plus h minus f of x, which will be am x plus h power m plus so on till a1 x plus h plus a0 minus am x power m minus a1x minus a0. And you can see here that the am x power m term will get cancelled and the expansion will have the second term onwards here. So that will be m times h am x power m minus 1 plus lower powers of x. So you can see that the first order difference is becoming a polynomial of degree m minus 1, right? Similarly, the nth order difference will be a polynomial of degree m minus n. And we can say that the m minus 1th order difference of this function is a linear polynomial. It has degree of m minus 1, so the degree comes out to be 1. And the first term of that is, you can evaluate it from the general formula. The first term of that will come out to be m factorial h power m minus 1 am into x. This is the m minus 1th order difference, right? And mth order difference of f of x will be coming out to be a constant or a degree 0 polynomial, and that will be m factorial times h power m am, right? Now, any higher order difference will be identically equal to 0. Therefore, what we can conclude from here is, from the original formula, if you see, the original formula was delta nh f of x is equal to summation n I goes from 0 to n minus 1 power n minus I and nci f of x plus ih. This was the original formula, and now we have taken some special cases of that formula for the function f of x, which is a polynomial of degree m, like this. We have evaluated the special case for this particular situation. So we can say that the mth order difference here correct is coming out to be um, so in this formula, if I take h as 1, the step size is 1, we'll get delta n1 f of x is equal to summation I goes from 0 to n minus 1 power n minus I nci f of x plus h, x plus I, f of x plus I, and f of x plus I. And f of x plus I was simply okay. So this was the nth order difference. I am going to put m in place of n because I am taking mth order difference here, right? So I'm going to say summation I goes from 0 to m minus 1 power m minus I mci f of x plus I, right? That is equal to this value, right? That is equal to this value, correct? So we have gotten the mth order difference of this function I goes from 0 to m minus 1 power m minus I mci f of x plus I is equal to, we got 0 if m is less than n and m factorial am if m is equal to n, right? So from here we can take f of x as x bar m, and let's take x is equal to 0 in this formula. We will get the Euler identity that is sometimes important in problem solving. So we'll get I is equal to 0 to n minus 1 power I nci I power m is equal to 0 if m is less than n and minus 1 power n factorial if m is equal to n. So this is an Euler's identity that is proven by using the formula for the nth order difference and applying it to a special case of this polynomial f of x is equal to x power n at x is equal to 0 and using step size h as 1, right? It doesn't matter so much in particular problems, like I'm just showing you this because it's an interesting result. The main idea that you need to keep in mind is that when you take mth order difference of f of x and f of x was a polynomial of degree n, the difference will be a polynomial of degree n minus m, right? So if your if m is greater than n, the difference will be 0, right? So that is the basic idea that we are using here. The main formula for the whole section is the general formula for an nth order difference, which was delta nh f of x is given as summation I goes from 0 to n minus 1 power n minus I NCI f of x plus IH. That is the general result. And the special cases of that we have already seen delta 1h, delta 2h, f of x, and so on. So we will see how to use this in problems. The next topic that I want to briefly touch upon is what is an integer valued polynomial. Integer valued polynomial. So this is different from when I refer to as an integer polynomial. We are not talking about the coefficients of the polynomial. We are talking about the output of the polynomial. So if the value or the output of a complex coefficient polynomial f of x is an integer when x is an integer, then f of x is an integer valued polynomial. So what does this definition tell us? So whenever you give input as x, which is an integer, to a polynomial, if the output also turns out to be an integer, then such a polynomial is known as an integer valued polynomial, right? So all polynomials in z of x are obviously integer values. You should understand why. Because the coefficients themselves are integers. So if you give an input which is an integer, the answer has to come out as an integer, right? So we can also have integer valued polynomials of any positive degree with non-integer coefficients. So it is not necessary for an integer valued polynomial to always have integer coefficients. It is possible to take a rational coefficient and still create an integer valued polynomial of any degree. So we'll take some examples and show you what we are talking about. So the polynomial, let's say we are writing x choose k, xck. So the expansion of this is this, x minus 1, x minus 2 till x minus k plus 1 divided by k factorial, right? Now here k is a positive integer. By looking at the product on top, you should realize that this is a xck is degree k polynomial, and also because it is a product of k consecutive integers, we know from number theory that it is divisible by k factorial. So basically we know that it is guaranteed that xck is an integer as long as x is an integer, right? So therefore xck becomes your typical kth degree integer valued polynomial. Right? That becomes a typical kth degree integer valued polynomial. Notice that if you split it out and write it in a regular polynomial form, the coefficients will be rational numbers. Also from combinatorics, we know these properties that xck plus xck minus 1, this is the Pascal's triangle property, is equal to x plus 1 ck. Therefore, we can say x plus 1 ck minus xck is equal to xck minus 1. And what is this? This is actually the difference of f of x plus 1 minus f of x. So this is like saying first order difference of xck, right, is equal to xck minus 1. Our notation for difference of functions was this, where this was the first order difference of function f of x, which was f of x plus h minus f of x, and the step size here was h. Here what we are doing is we are taking the step size as 1, right? So then what will happen? You will get f of x plus 1 minus f of x. And what is f of x plus 1 in this case? It is x plus 1 ck minus x ck, which is equal to x ck minus 1 by Pascal's triangle, right? Okay, the next point is basically a sufficient and necessary condition for an nth degree, polynomial in C of x in complex numbers to be integer valued, is that it can be expressed, the polynomial should be expressed in the form an times xcn plus an minus 1 times xcn minus 1, and so on, a1 times xc1 plus a naught, where a1, each ai are integers, right? Each ai is an integer and an is not equal to 0. So basically what we are saying in this property is that using functions like xck, which was a kth degree polynomial, the kth degree integer valued polynomial, we can construct any nth degree integer value polynomial that we want, right? So for an nth degree polynomial, we just said an times xcn, an minus 1 times xcn minus 1, and so on. So this forms like the basis set using which we can construct higher order integer polynomials, integer valued polynomials, right? Now let's apply the three things that we have learned. We learned Lagrange's interpolation, we learned about difference of functions, and we learned about the integer valued polynomials. Let's see how we can apply them in problems. So question 1 is this: suppose an nth degree polynomial satisfies f of k is equal to 1 by n plus 1 ck, where k goes from 0, 1, 2 till n. We have to find the value of f of n plus 1. Now there are two ways to do this question. The first approach is Lagrange's interpolation, because notice that we have n plus 1 values of f of x at n plus 1 different points. These are given to us. So we can obtain f of x of degree n by Lagrange's method, right? So what is that method? We will say that f of x should be equal to sum over k goes from 0 to n for each of those xi's. These are my xi's. My yi's will be 1 by n plus 1 ck. So we'll say f of k, this is my yi, and for each yi I have to do a product such that I is not equal to k and I can be anything from 0 to n except k basically. And on top you have x minus I, denominator you have k minus I. And this is what we have to do as a product, right? So basically if I was 2, we will say x minus 1, x minus 3, not x minus 2. And here we will say k minus, k will be the y value for that particular point, right? So k is the limit of summation. So when you fix the k, you will do the product here, right? This is what the formula that we had written earlier in a long form. This is the same formula basically. So if you evaluate it, you can show that f of m here would be summation of k goes from 0 to n, k goes from 0 to n, f of k minus 1 power n minus k, m into m minus 1 till m minus n by m minus k, k factorial, n minus k factorial. You can try and prove this yourself. Try to find the summation here. You will get summation k goes from 0 to n minus 1 power n minus k, f of k, m c k, and m minus k minus 1 c n minus k. This is what comes. I am skipping some steps. You have to work it out yourself. If you put m is equal to n plus 1 in this, because we need f of n plus 1 finally, put this in this formula, you'll get f of n plus 1 is equal to summation k is equal to 0 to n minus 1 power n minus k, which is equal to 0 if n is odd and is also equal to 1 if n is even. So that becomes our answer by the Lagrange interpolation method. However, a more intuitive method is the difference method that we had seen earlier. So we know this is method 2. So we know fx is nth degree, right? Nth degree polynomial. So that means so n plus 1th order difference of f of x must be equal to 0. So what we want to calculate is delta n plus 1 h f of x, right? Now what was the formula? Our formula was delta n1 f of x, nth order difference with step size 1 was equal to summation I goes from 0 to n minus 1 power n minus I f of x plus I multiplied by nci. This was the summation. What we will do here is we'll replace we will basically replace here n with n plus 1, right? Because we need a n plus 1th order difference. Also, we'll take step size h as 1. H is 1 in this result. We have already put that there, right? And we can also take x is equal to 0 because our starting point was f of 0 was also given to us, right? Yeah, I think f of 0 was also, yeah, f of 0 was also given. So what we get is summation I is 0 to n plus 1. This is minus 1 power n plus 1 minus I, f of 0 plus I, right? So this is nci f of I, right? Now this should be equal to 0 because this was my n plus 1th order difference. This should be equal to 0. So we already know f of I values for I goes from 0 to n, right? And f of I values was 1 by n plus f of I was equal to 1 by n plus 1 ci. So notice that here we had, I have made a mistake here. This is not nci, it is n plus 1 ci because we had to replace in the original formula it was NCI. This was the original formula. But when you replace n with n plus 1, you should get n plus 1 Ci here. So notice that n plus 1 Ci times Fi is equal to 1. Right? For each time n plus 1 Ci, each value of I, you'll get Fi is corresponding 1 by n plus 1 Ci, right? So this part is anyway cancelling. So we can say that the summation was going from 0 to n plus 1. I can break it down into two summations. When I goes from 0 to n, 1 minus I, and this part becomes 1, plus when I is equal to n plus 1. In that case, we have n plus 1 C n plus 1 f of n plus 1. That will be equal to 0. I'm just splitting this summation over n plus 2 terms into n plus 1 terms and the last term, right? So we know this, that this value will be either 0 or 1 depending on whether the number is even or odd, right? So from there, what we get is fn plus 1 is equal to 0 if n is odd and is equal to 1 if n is even. So even though it looks complicated, this is a very easy solution because we are directly using the formula for the n plus 1th difference, order difference, right? And we are evaluating that at x is equal to 0 and directly saying what is the value of that, that is 0. So from there we are able to find f of n plus 1, right? So think about it. You have two alternative methods, the difference method and the interpolation method. You can use that, both of them in problems. Let's look at another question. Let f of x be a polynomial of degree n, which satisfies f of k is equal to 1 by k for k goes from 1 to till n plus 1. We have to find the value of f of n plus 2. Okay. So obviously the same method, interpolation method and also differences method are still valid. You can use the same two methods that we discussed previously in this question as well. However, there is a simpler and direct way. We'll use the direct way. So consider a polynomial of degree n plus 1, and that is called your g of x. G of x is defined as x times f of x minus 1. So g of x is defined as x times f of x minus 1, and because f of x has degree n, g of x has degree n plus 1. Now you can see here that g of x equal to 0 has n plus 1 roots. Basically, all the roots are when x could be 1, 2, till n plus 1, right? So there are n plus 1 roots of g of x, and because g of 0, what is the value of g of 0? Put that here. You get g of 0 is minus 1. Because g of 0 is minus 1, we can now say that g of x, since it has n plus 1 roots and the roots are these, we can always write it as a times x minus 1, x minus 2, till x minus n minus 1. And now we use the value of g of 0, which was minus 1, which is equal to a times 0 will become minus 1, minus 2, till minus of n plus 1. So the number of terms here becomes minus, it is n plus 1 term. So it is minus 1 power n plus 1, n factorial a is equal to minus 1, right? So finally we get a is coming out to be minus 1 or plus 1 by minus 1 power n factorial. That is becoming our value of a after simplifying, and therefore we get the g of x function. G of x function is simply x minus 1, x minus 2 till x minus n plus x minus n minus 1 divided by minus 1 power n plus 1 factorial. And now if you put g of n plus 2 here in it, you will realize that the value will become, if you put n plus 2, the top part becomes n plus 1 n till 1. So it is n plus 1 factorial divided by n plus 1 factorial. So that is simply going to be minus 1 power n, right? You're going to cancel this n plus 1 factorial from there. So you're getting g of n plus 2 is equal to this. And now f of n plus 2 was what? F of n plus 2 was defined as uh, basically we had g of n plus 2 is equal to n plus 2 f of n plus 2 minus 1, right? So g of n plus 2 we already know. You will get minus 1 power n plus 1 divided by n plus 2 is equal to f of n plus 2. Now that means that f of n plus 2, if n is odd, f of n plus 2 is 0, and if n is even, it is equal to 2 by n plus 2. So we are solving the problem by choosing the appropriate g function. We chose our g function intelligently and we were able to get it, right? Okay, let's look at another final problem here. Okay, so let f of x be an nth degree polynomial satisfying f of k is equal to 2 power k, where k goes from 1 to till n plus 1. You have to find out f of n plus 3. Okay, so we know that f of x has degree n, so it follows that its n plus 1th order difference must be 0. Order difference is equal to 0. So we'll apply the formula here again. Delta n plus 1 f of x will be equal to summation I goes from 0 to n plus 1 minus 1 power n plus 1 minus I nci f of x plus I, and that must be 0, right? Now we can take x is equal to 1 here, take x is equal to 1 and substitute values of f of k is equal to 2 power k for k is equal to 1, 2 till n minus n plus 1, right? Once you do that substitution, you will be finally able to find out the value of f of n plus 2 from here. Expand this summation, put all the numbers, you should be able to find f of n plus 2, and f of n plus 2 comes out to be 2 power n plus 2 minus 2. We are using the difference formula to get f of n plus 2 because we know the difference is equal to 0. Once you have f of n plus 2, we can use the formula again, use the same formula again, but this time you can take x is equal to 2 here, then you will end up getting f of n plus 3 from there. You will expand the summation again, but you're using x is equal to 2, so the summation will go up to f of n plus 3, and you'll get f of n plus 3 is equal to 2 power n plus 3 minus 2n minus 6. So this method, I have not shown you all the steps of the calculation, but the idea is the same. We are using the n plus 1th order difference. However, there is an alternative method also, which is quite interesting and uses the concept of the integer valued polynomial that we saw earlier, right? So what is this method? So we can say that the function g of x is equal to twice of x minus 1 c0 plus x minus 1 c1 so on till x minus 1 ck cn. En. This is clearly a polynomial of degree n. Polynomial of degree n. Because x minus Cn, x minus 1 Cn has degree n, right? So the sum of all of this will have degree n. Now, obviously, we can see from here, by using combinatorics, we can see that the sum of the terms here from 0 to n, x minus 1 C0, x minus 1 Cn, will be equal to 2 power x minus 1, and outside there is a 2. So this whole thing will be equal to 2 power x, where x goes from 1 to n plus 1, right? X is going to go from 1 to n plus 1 because you need the whole thing to go from 0 to n. The superscripts should go from 0 to n, right? Great. Now, we know that f of x had values of what? F of x had values of 2 power x for x going from 1 to n plus 1, right? This was given in the problem itself, so we can see that f of x and g of x have same values at n plus 1 points, whereas we know that f of x and g of x are degree n polynomials, right? So that means f of x and g of x must be identical. The only way that f of x and g of x can have the same value at more than n points is that they are identical. F of x is equal to g of x, right? So now we can easily calculate f of n plus 3, because for us now f of n plus 3 is same as g of n plus 3. And what is g of n plus 3? That is equal to twice of n plus 2 c0 plus n plus 2 c1 till n plus 2 cn. And this part is equal to 2 power n plus 2 minus n plus 2 cn plus 1 minus 1 and twice outside. So this becomes basically 2 power n plus 3 minus 2 times n plus 2 minus 2. So it is minus 2n minus 6, right? That becomes your value of f of n plus 3. So again, we have seen two alternative methods. One is guessing a nice function. The other is the difference method that is already discussed. So that concludes our video here. We have discussed interpolation, we have discussed finite differences of polynomials, and lastly, a little bit on integer valued polynomials. So hopefully you will be able to apply these concepts when you encounter problems like this. So see you next time.